When we have several unstationary variables and they are not integrated, what we can do is to estimate a vector autoregression model. So the first step is to transform those non-stationary variables to be stationary. Usually we use first differencing. Then we estimate the regression model or vector autoregressive models from the set of I1 variables derived from the first step. Let's use an example to illustrate how to estimate a VAR model. We now have real personal disposable income, that's Y, and real personal consumption expenditure, that's C. If we perform a unit root test for both Y and C, we can find that, okay, for the variables at levels, both of them are not stationary. So the p-values are greater than 5%, which means we cannot reject the null hypothesis of unit root. However, after we take the first difference, both variables actually pass the unit root test, both of them stationary. And we can also check for co-integration between those two variables. So we estimate a linear regression model between C and Y first. Then we derive the residual term. Then we perform a unit root test on the residual term. Then we notice that, okay, the critical value is minus 3.37, and the test statistics is larger than it. So it's not in the rejection region. We conclude those two variables are not co-integrated. I would like to draw attention to the fact that even if we are performing a unit root test here, the critical value here is not the standard DF test critical value. It's from the co-integration test critical value table, which can be found from top 2 selection nodes. So before we go ahead to estimate the model, let's have a look at the time series chart first. If we plot these two series together, left-hand side, that's the variables on at levels, and right-hand side, those are first difference variables. You may be surprised to find out those two time series actually are moving quite close to each other over a long period of time. So that's from 1960 all the way to 2010. It looks like almost the two lines are parallel to each other. However, the co-integration test shows that they are actually not moving together. The difference is larger than the test can tolerate, put this way. And of course, after taking the first difference, you may notice that the first difference series are much more stationary based on the pattern. It looks almost like a random walk. So the takeaway from this example is sometimes even if two time series looks like they are co-integrated, it might not be the case. It's always safe to perform a test to numerically verify whether the visually identified pattern is valid or not. Okay, we use a test to select lag length, and we determined that the lag length should be 1 for this VAR model. Later in the stata demonstration session, I will show you what commands to use in order to choose the optimal lag length for a VAR model. But here, let's look at the coefficient estimate first. So for both models, we have a coefficient estimate for the lag terms of delta C and delta Y. So we can interpret the results in this way. So past changes in C have positive effect on current changes in both C and Y. So we have a positive coefficient loadings on delta C t minus 1. And that is 0.215 in this first equation. So that's CT, changes in CT's impact on its own. The second coefficient is also positive. Is 0.475. That's changes in CT, has the impact of changes in CT on delta YT. And we also find that past changes in Y have positive effect on current changes in C, but negative effect on Y. So on itself, that's negative, but on C, that's positive. So this is how to interpret the result.